So yesterday we had no repetition, but today we have repetition. So we have permutations with repetition, and that's where the same number or the same letter or the same object appear more than once. So for example, if we look at the word tooth, has two O's in it, and it has two T's in it. So we have two repeating two items. So to calculate that permutation, we have to take into account that they can be repeated. So here's the formula. We take our normal permutation, the NPR, and we divide it by x1 factorial, x2 factorial, etc. Okay, so x1 is the first repeating object, or x2 is the second repeating object, x3 is the third repeating object, etc. X is the number of times object repeats. Okay, so for this particular problem, tooth has 5 letters, so N is 5, and we want to arrange all of the letters, so R is also going to be 5. X1 is the first repeated, which is the T, and there are 2 of them. X2 is the second repeated, which is O, and there are 2 of them. And then if we had, like, I don't know, if there were repeating H's, we would do that as well. So for this formula, we have 5p5 over 2 factorial 2 factorial. And 5p5 is 5 factorial because they're the same. Oops, there's 2 2's there. And you can actually enter this into your calculator all at once. Hold on one second and I'll pull it up. You would want to put parentheses 5 factorial divided by, and then parentheses 2 factorial times 2 factorial, like that. So when you enter it, that's how it enters into the calculator. It's actually easier on the Apple than it is. Oh, no, it won't work on that. Okay. So you actually end up with 120 divided by 4, so it's 30. So there are 30 ways that you can rearrange the word tooth. And what this does is, because if we rearrange it like O-O-T-T-H, this is the first O, second O, we could also do the second O, first O, but that doesn't count as something different. And so that's what this does. By dividing by those factorials, it takes out the repeats. Does that make sense? How many different 5-letter arrangements can be formed from the word apple? Okay, so there's 5 letters in the word apple, so n equals 5. We want 5-letter arrangements, so R is 5. And we're using letters that repeat. There's 2 P's. That should be a sub 1. So that's x sub 1 equals 2. Okay, so to calculate how many different arrangements, we have 5p5 over 2 factorial, because there's only the one letter that repeats. So this is 5 factorial over 2 factorial. And I'm going to do this the long way for a second. And you can see the 2's will cancel. So I have 5 times 4 times 3, which is 20 times 3. So there are 60 different ways to rearrange the word apple. Crazy, isn't it? Try another one. We have how many different 6-digit numbers can be written using the following 7 digits? And we're going to assume all the repeated digits are used. So we want 7p6 for that because we're going to use 6 of the 7. And then we have 2 3s and 3 4s. So 7p6 divided by 2 factorial, 3 factorial. So I'm going to use my probability function in the calculator. And 7p6 is 5040. 2 factorial is 2, 3 factorial is 6. So I'm going to divide that by 12, and there are going to be 420 possible arrangements. Here's one that you guys might like to know. If you have 4 chocolate chip, 2 oatmeal, and 2 double chocolate cookies in a box, how many different ways can you eat those 8 cookies?
How many ways?
How many different ways can you eat those 8 cookies? Okay, so there's 8 cookies. Okay. You have 4 chocolate chips, so we'll say x of 1 is 4. You have 2 oatmeal and 2 double chocolate. Okay, and we're going to eat all 8 cookies, because why would you only eat 7 or 6 cookies, right? You're going to eat all 8.
I eat 2 chocolate chips, 1 oatmeal, 1 double chocolate, all together, like mushed up all together.
Okay, so we've got our 8 factorial over 4 factorial times 2 factorial times 2 factorial. 8 factorial. Let me use this calculator this time. Is 40,320. 4 factorial is 24, and then 2 and 2. So 24 times 4 is 96. So I have 40,320 divided by 96. Let me just double check myself on that, because yep, okay. There are 420 different ways to eat these 8 cookies.
8 cookies.
Yep, 420 different patterns of eating the cookies.
420.
How did I do what? 40,000. Whenever these two numbers match, it's just the factorial of that number. And so I put it in the calculator. I pushed 8 and then the exclamation, and it gave me the 40,000. Now, when they don't match, it's a different formula. When they don't match, just remember, okay, when n equals r, NPR is n factorial. When you have NPR and n does not equal r, you have n factorial, no, wait. Okay, so it's n factorial over n minus r factorial. So because these both matched, we just did 8 factorial, which remember is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 technically, but really the times 1 doesn't matter. So that's the calculations there. Okay, so a combination, remember the difference between a combination and a permutation is the order doesn't matter here. So if I have a menu and I'm trying to decide what to eat, there's 15 different entrees, 12 different sides, and 4 different breads. Doesn't matter which one I pick in what order. I can decide on the bread first and then decide on the side dish and the entree, or I could decide on the side dish and then the bread and then the entree. You know, it doesn't matter what order I pick them. What matters is that I pick them. So the order won't matter. So when we have order mattering, like a digits of a security code, then you have a permutation. But when the order doesn't matter, it's a combination. So combinations have no regard for order, and there's no repetition. Okay? And here's the formula. It's very similar to a permutation, but we add the r factorial to the outside. And that's because with a permutation, it can only go in a certain order, but in a combination, you get all the orders. I did it again. Okay, so if we're going to calculate, these should be small, sorry, 7C2 like that. Using this formula, we have 7, let me change from red. So 7C2 is equal to 7 factorial divided by 2 factorial times 7 minus 2 factorial. So that'll give me 7 factorial over 2 factorial times 5 factorial. So if I were to write this all out, I have 7 times 6 times 5 times 4 times 3 times 2 times 1 over 2 times 1 times 5 times 4 times 3 times 2 times 1. And these all cancel. And so I have 42 over 2, which gives me 21 possibilities. Now if I'm using the calculator for this, instead of writing everything out, 7 factorial is 5040. So I get 5040 over 2 times 5 factorial, which is 120. So that would be 5040 divided by 240, which is 21. Same thing. So not using the calculator at all. I didn't use the calculator at all for this. I just, wrote them out the long way and then I canceled. And 42 divided by 2, so that's 21. Or using the calculator where I plug in the factorials and then multiply and divide. Okay. How many ways can 3 desserts be chosen in any order from a menu of 10? So, like those tapas places where you order little tiny hors d'oeuvre sizes of everything? Have you guys heard of that, tapas? They're not, you don't get like a full meal, you get like little bit of this, a little bit of that, a little bit. So this would be like a tapas dessert, you get to pick 3 out of 10 of them. So we have 10 desserts and we're going to choose 3. So I have 10 factorial over 3 factorial times 10 minus 3 factorial. So again, I'm going to work this out the long way. That's the 10 factorial, and this would be 7 in the denominator. So I have a 3 factorial, so 3 times 2 times 1, and then a 7, which is all of this. And the 7 stuff is all going to cancel out here and here. So I have 10 times 9 times 8, which is 90 times 8, which is 720, I believe. Let me just double check myself. Yep, 720 over 6, which is 120. So there's 120 different ways to choose dessert off of this menu of 10. You get to pick 3. And again, if you were going to do this just in the calculator using the factorial button, you'd have 10 factorial over 3 factorial, 7 factorial. So 10 factorial is 3,628,800 divided by 6 times 7 factorial, which is 5040. So 3,628,800 divided by 30,240. 120. So you can see, like, even though the calculator did all the big numbers for me, it was actually faster for me to do it without using the calculator. So it just depends on what. Okay, this is when you have, or sorry, there's two more example problems. This is when you have two separate groups and we need to figure out the combination, okay? So 12 boys, 14 girls. So we have two groups, boys and girls. Okay. For the girls, we have 14 girls and we want to choose two of them for the group. So that's going to be 14C2 because it doesn't matter what order we choose the two girls. We just choose two girls. And for the boys, we have 12 of them, and we want one in the group. So that's 12C1. Okay, so this is 14 factorial divided by 2 factorial times 14 minus 2 factorial. And this time I'm not going to do all the long way. So it's 8.71782912 times 10 to the 10th. And then 2 factorial is 2. And that's 12 factorial, which is 479001600. So 479,000,001,600 times 2. And then I'm going to divide the first one by the second one. And I'm going to get 91. So there's 91 possibilities of choosing the two girls. Now this one would have actually been, if I had written it all out, easier because I would have had, by the time I was done canceling, I would have had 14 times 13 over 2 times 1 because all the 12 would have canceled. So this one would have actually been easier to do the long way. Okay, then I have 12 factorial over 1 factorial times 12 minus 1 factorial. So 12 factorial is 12 times 11 times 10, all of those numbers times 1. And then I have a 1 factorial. And then 12 minus 1 is 11 factorial, so that's 11 times 10 times all this times 1. So those will all cancel. And what I end up is with 12 divided by 1. So there's 12 ways to choose the boys. I did not need to work that out. If R is 1, then there's only 12 different ways to pick one person out of 12, right? So like if I had 20 people, but I want to pick one of them, there's only 20 ways to pick that one person. Does that make sense? So if R is 1, you don't have to calculate. This is just your number right here. Okay, so now I need to figure out to pick the group. Okay, I take the girls times the boys. So that is 91 times 12. So there are 1,092 ways to create a group of 3 with 2 boys, or 2 girls and 1 boy from this classroom. Okay, we have 18 Democrats and 20 Republicans are in a committee, and we're going to make a subcommittee with 3 Democrats and 4 Republicans. So Democrats, we'll have 3 Democrats out of 18. Sorry, I wrote that backwards. 18, and we want 3. And Republicans, we have 20 and we want to pick 4. So this is 18 factorial divided by 3 factorial times 18 minus 3 factorial. I'm actually going to move this down a little. So this is 18 times 17 times 16 times 15 times 14 times 1 over 3 times 2 times 1 times, and then 18 minus 3 is 15, so I'm from 15 down. And then times 1. All of these cancel. So I end up with 18 times 17 times 16 over 3 times 2. So that's 4,896 divided by 6. So there are 816 ways, guys, 816 ways to pick Democrats. To pick Republicans, we've got 20 Republicans and we want 4 of them. Okay. 20 times 19 times 18 times 17, 16 here. So my 16 down and this 16 are going to cancel, so I'm just going to leave them out. Does that make sense? And then 4 times 3 times 2 for my 4 factorial. So I have 20 times 19 times 18 times 17 is 116,280 over 24. So 4,845 ways to pick Republicans. And so for the subcommittee, we're going to do Republicans times Democrats. So 816 times 4,845. And we're going to get 3,953,520 different ways to create this subcommittee. And that's why nothing gets done.